Friday IACS seminar series. My name is David Sondak. I'm a lecturer in the Institute for Applied Computational Science. Just so everybody knows, we'll be here again next week on the 28th for a talk on natural language processing, and so just put it on down on your calendars. Today we have Nick Malaya from AMD. Nick is the AMD technical lead for the Center for Excellence, working on the Frontier Exascale supercomputer. Nick got his PhD at the Odin Institute for Computational Engineering and Sciences. That's when we met each other and became buddies. And before that, he did his Master's of Science in Mechanical Engineering. I'll let Nick take it away from here. So welcome, Nick.
Hello. Does that sound good?
Did you turn the...
It did. Okay. Can you hear me? Is it coming through the mic? Very good. All right. So first of all, I just wanted to say thank you very much for having me on your busy Friday afternoon. And so I've given this title here, Preparing Scientific Applications for Exascale Computing. And what I'm going to do today is I'm going to talk through kind of a few different use cases. I am at AMD. It's an industry. My background was academic. I did my PhD in computational science. And now I work in the research organization for a hardware company. So you might ask why someone who did computational fluid dynamics, uncertainty quantification, things like that ends up at a hardware company, and hopefully after this talk you'll see why. But so the agenda I have here is to motivate the importance of scientific computing, high performance computing, kind of things I just use interchangeably. I'll discuss Frontier, which is very exciting. This is what I'm working on from an application standpoint. We expect it to be the largest computer ever constructed. And then I'll discuss some of the scientific applications we will be running on Frontier. We're not building a big computer just for fun. That sounds fun. But we're actually doing it for real scientific impact. And then finally, I'll talk about some of the themes that I see kind of in the future of scientific computing, particularly the synthesis of high-performance computing and what people call AI or machine learning. So I'll start with a fun one. This is something that actually, even when I heard I was giving this talk, I hadn't come up with yet because it's very timely. Does anyone see this press release? Anyone know what this is, perhaps, is a fun way to put it. And I'm not expecting there to be too many biochemists here, but what this is a S230. It's an antibody. It was known to neutralize the SARS coronavirus, which occurred, I think, in 2003, some time ago. And what this is a molecular dynamics simulation of that antibody applied to the novel coronavirus that you may have heard of that has hit the news so recently. So I think this is a wonderful example of the importance of scientific computing. This is a computational simulation. It is not an actual model, not an actual examination of this. So it's not, for instance, using X-ray crystallography. This is very timely because, as we all know, oh, sorry, I forgot. This is not my work. I'm collaborating with folks at Livermore National Lab, but I just thought it was a nice motivation. But so the virus was identified on December 31st of last year, at least publicly identified. There's some debate about if it was known to the Chinese authorities earlier than that. But it certainly was first mentioned on December 31st, and yet on February 3rd of 2020, this simulation had already been performed. So what's going on here is that we have a novel use of HPC. It is a timely thing. There are people who are dying from this virus today. There is a great interest in our society to develop antibodies or vaccines against it. This is done in a faster way than you could do with experimental methodologies. It was done on the Corona cluster, which is an AMD cluster. It has AMD GPUs at Lawrence Livermore National Lab. It is a remarkable coincidence that this happened. It wasn't designed for it or anything like that. It just happens to be called Corona, and the coronavirus showed up. It was, in fact, installed far before the novel coronavirus became prevalent. As I mentioned, it uses a common open source package, OpenMM, which is a molecular dynamics package that I'll talk about NAMD later in this talk. Another thing that's kind of novel here, the antibodies that worked on SARS, there's an open question of will this also work on the novel coronavirus. They have done some structure, so they have some sense of the structure. That's what's shown in blue. And the question of if the antibodies will actually bind to it effectively is what's being tested here. But in addition to that, the research team is using machine learning as a sense to sample the parameter space. They're saying, are there slight differences in the antibody that would make it bind better? And they're sampling this space efficiently and trying to basically preempt research teams in what will we do to develop a vaccine. So pretty timely, exciting sort of use. High performance computing very much center on stage here. And this is all just to motivate that simulations are prevalent now. They're absolutely pervasive. I don't think I need to sell this crowd on it. But every field of human endeavor in science and technology is informed by simulation at this time. The Boeing 787, similar to what we were talking about previously, it was designed on computers using computational fluid dynamics, material science and such, many more times, iterated, optimized to optimize the lift, to minimize the drag, much more than they designed it and built it and validated in wind tunnels. It's a key computational tool. It would be very expensive for Boeing to have built that many planes, right? They probably should have done this a little more for the MAX, but that's a different talk. Yeah. Drug discovery, we just mentioned. Societal impact, global warming. We can't simulate global warming, right? We cannot actually build an experimental lab and do it. This is an area in which it would otherwise be inaccessible to us unless we wanted to build a planet, run it for a few million years, and see what happens, right? It'd be too late.
Not to like, I don't mean to
Quibble.
Disruptive way, but like, isn't part of the problem with the Mac that the software was good like 99.9% of the time, and the 0.1% or whatever the time that the software, call it simulation ecosystem, didn't exactly mimic the conditions, a bunch of people died.
Yep.
So, I mean, not to be too glib about it, but software doesn't always get everything.
No, software, let me be clear, is not a panacea. And actually, I think this does not appear in this talk. I have worked in this field of uncertainty quantification. I think that's an absolutely essential thing. For those of you who are data scientists who are not working on something where you worry about a plane crashing, you need UQ as well. It's something I will not jump off into a tangent here, but I completely agree with you. The field of scientific software is not nearly robust enough and nearly as rigorous as it should be in terms of establishing these kind of credibility intervals and such. So full-fledged point. But I claim that in the case of something like computational aided design, it will improve it if we use it effectively, much more so than designing planes in a wind tunnel and testing it. I'm not suggesting we should actually remove that step either, which some people say. Tangentially, if you're a data scientist and you're saying that we should remove people from the loop, I also think you're wrong. I think people are an essential validation step of it. We're not going to remove the human element. I'm not going to take all your jobs with the GPU. I'm very serious about that. It's not a Terminator situation. This is augmenting human thought that way. So it's a good point. And to that point also, feel free to interrupt. Let's talk. I'm happy to do so. We have some buffer time here. But so actually, I'll just throw one other one that's fun in there. The gravitational waves, which we heard about, was an experimental apparatus, right? They used these interferometers that were actually in space measuring gravitational waves. But the Nobel Prize winning work actually involved some of the computational effort, the post-processing and stuff. So even if you are thinking of experimental facilities and such, ultimately you are still tying it very closely to computation. And these simulations are often time sensitive. Hurricanes, if we model a hurricane and it takes us a month to run the simulation, it's probably not enough time for us to evacuate the right places. But there's a variety of timescales that matter. There's throughput. We just want to run more simulations because we are optimizing over a parameter space. Those might only take a minute, but if we actually need to optimize billions of different models, a billion minutes serially is actually a very long time. Coffee time. All of us have done this. You have something running, you're installing something on your laptop, and you go up and get a coffee. That's disruptive, right? It actually is something that's an impediment to you doing productive work. Overnight. If you can't run overnight, you go home, you run your job, you want it to be done in the morning. So there's various length scales. Mean time between failure, MTBF. If you can't run a job long enough before your computer might run out of batteries, things like that, these are disruptive. All of this is trying to build to the point that we need more and more compute. We want to get solutions faster and faster. No matter how much compute, I claim, no matter how much compute I give you, you will find a productive use for it. I'm at a hardware company. I sell more devices when I do that, so I'm a little incentivized for this. But I would show you some data here. I think this is from OpenAI. It's a very nice plot that shows the 300,000-fold increase in compute that has occurred since, if you can see those axes, 2013. HPC system performance doubles. It's a power law. It doubles at roughly 1.2 years, every 1.2 years. It's actually faster than Moore's law, if you look at it, because of the way we've parallelized them. But machine learning models have been doubling every 3.5 months. So again, this talk is about scientific computation. Those of you who are into AI and machine learning also have a reason to pay attention, because I believe that everything I tell you here will trickle down into that very soon. By the way, this plot, when OpenAI did it, was in 2019. It is now 2020. It doesn't have transformer. It doesn't have Ernie. Any NLP people here? Those have substantially more parameters than any of the models shown here. So I forget, AlphaGo 0 had a, doing this off the top of my head now, but it had less than 1 billion parameters. And BERT and Ernie, if you're familiar with it, there was BERT, which was an NLP model, and then someone, of course, it's a very fast-moving field, a week later published Ernie. Those have trillions of parameters. So they're just compute hungry. Some of these machine learning models take a month to train, and on hundreds of GPUs. So substantial amounts of compute. So hopefully I've got your appetite whet now for saying we all need more compute. That's what I'm here to talk about, the beginning of the exascale era. Exascale here being 10 to the 18. It's a SI prefix, or a million, nice kind of handy way to think of it, and flops. So when we say exascale, we really mean flops. And flops are floating point operations per second. This tends to be the aggregate number we look at when we measure a supercomputer's capacity to do compute. It's in a poor man's fashion, and you could imagine that humans do a flop or two. So you can do a compute per second. This can do a million per second. So I was part of the team at AMD. I actually, in addition to being a research scientist, I was the performance lead for our Coral 2 bid that won this machine. It was a part of Cray, now part of HPE, Hewlett-Packard Enterprise. And this is a grant from the United States government, Oak Ridge National Lab, to build this computer, which they are calling Frontier. So some fun facts. This comes from our friends at Cray. This is the sort of thing that happens when you give marketing people information about a big computer. But it's nevertheless sort of fun. The network bandwidth on the Frontier system is 24 million times greater than the your home internet connection. So you could download 100,000 HD movies in 1 second. There's that guy in the dorm who will do that sort of thing, you know, so he could use it. If 7.7 billion people on Earth, the entire human populace, I believe, completed one calculation per second, it would take 6 years to do what Frontier can do in 1 second. So a lot of compute capacity here. It'll cover over 7,300 square feet. That's almost 2 basketball courts. Gives you kind of a sense of the size. It's actually not unprecedented for supercomputer sizes. It's actually getting smaller and denser. The reason, actually, is the speed of light. The closer you can get to things, the shorter your latencies. And we hit that a lot. The speed of light is a thing we think about and architect for very much so. And it takes 90 miles of cables. There's a lot of interconnect. We want things to be connected to each other so that they can talk to each other in very efficient and high-dimensional ways. So it's the distance from Philadelphia to New York City. I should have changed that from Boston to some remote location. So I've mentioned flops. If you look at the current top 500, this is the ranking of supercomputers. I pulled this down. You can see NVIDIA's computer, our major competitor. Summit and Sierra are the 2 top computers there. The axis is about 200,000 petaflops. These are the 2 largest computers in the world. Summit is, by the way, a computer at Oak Ridge National Lab. And you see a bunch of other computers. I stand it out all the way to Stampede 2 because that was a computer I ran on very much during my PhD. It's still on the top 15 or so. And so if you were to project to what Frontier is, you can see where it's going. This machine will be in late 2021, which I am very aware of is very soon because I have a lot of work to do on this. But the reason I'm showing this is somewhat fun. I'm bragging a little and such. But actually, the point is that we are entering a new era, right? This is a different epoch. This is a different scale than we have encountered before. And when you scale out things, if you talk to people at Google, when they do large-scale data center installs and such, you hear the same things. When you reach a new scale you haven't hit before, things break, bugs introduce. You learn new things about where things work and don't. And that's what I want to try and capture more of here in this talk to kind of give you a sense of where we're going. And the real reason here is also, there's another one, and I meant to put this together, I didn't have a chance to. If you look at the top 500, well, you see the biggest computer, but if you look at the last computer, the 500th computer on the top 500, it tends to be a system that you could buy with a very reasonable faculty startup grant, startups, that sort of thing. So the point is, well, then you time lag it, and you say, how long does it take for the #1 system to basically become the 500th, accessible to all of us? It's about 10 years. So I'm giving you a window on where you will all be, even if you just go and work at any company, let alone a large-scale company, where you'll be in 10 years, and the challenges that you will certainly have to circumvent by then. And it moves fast, right? Power laws are a very good thing. They're great for compound interest. They're good for computing. So Frontier at a glance. Lots of words here. I won't go through all of it. I've mentioned some of it, but it'll be delivered in 2021. We're in a little bit of a race with Intel. Intel also is claiming they'll be in 2021, so we'll see who can win. They're a major competitor of ours. They're building a machine at Argonne National Lab. The government's very savvy about these things, by the way. They play you off against each other to get better bids, things like that. If you're a taxpayer, you should be happy about that. The peak performance publicly is stated to be 1.5 exaflops. It will be 100 cabinets. So again, a lot of density. Some machines have actually about 200 cabinets. So in some sense, it's a very dense and highly computed machine. And then I wouldn't be here if it wasn't, but they will be composed of AMD CPUs and GPUs. CPUs you're familiar with. They're in all of your computers. You also have GPUs, graphical processing units. It's sort of a funny thing. If you've taken linear algebra, you note that the things like translation, reflection, those sort of linear algebra things that might be useful for playing a game as a first-person shooter turning or so, also are the mathematics we use very commonly in science. They're matrices operations. And graphical processing units, which were constructed for gaming, have turned out to be extremely effective for scientific computations for the same reasons. So here's just a little picture, and I want to just show you again this kind of exponential increase that we're seeing. Titan, which was top of the line in 2010, was a 27 petaflop machine. Summit now, today, which is the most powerful computer that's known in the world, is 200 petaflops, and then Frontier is 1.5 exaflops, so about 7x. But you see, Summit is 256 cabinets. We're moving to 100 cabinets-ish. It'll have 1 CPU, 4 GPUs. I'll talk more about that. And you can see also that the system interconnect, you see it was 6.4 gigabytes, going to 25 gigabytes, now 100. If you look at the compute, I said, well, the compute's going up by 7, right? But the network is only going up by 4. So that might give you a sense of some of the bottlenecks that are happening. Everything's growing. Everything's growing at a power law, let's say. But when you have power laws, the exponent becomes very important. In fact, they diverge, right? One little difference, it grows. This happens in chaos theory. It's also happening here. So thinking about how we architect our systems for balance is very critical. And I claim it will have impact algorithms soon. So AMD's contribution of it, that was the full system. We are building the CPUs and the GPUs. I don't think I need to pound on this too much more. But it will have our custom CPU for it, custom GPU. These are actually compute engines now. They're no longer graphical processing units. You couldn't play games on them. They're specialized for compute. We just kind of call them graphics units because of a historical anachronism, largely. They're really more compute accelerators at this point. So this is more of an architecture slide, but I'll just show you. This is a modern server CPU. Has 64 cores, 128 threads, 256 megabytes of cache. Main takeaway actually from this that you want to see is this is about 2 teraflops of compute. Now I'll show you the GPU. These are what both exist today. These are not what will be in Frontier, but you can guess these numbers will go up. And here's a modern AMD GPU. And now I told you that the compute of the CPU was about 2 teraflops. Well, look, this is about 6.6 teraflops. You already have a substantially larger amount of compute. And you see if you're interested in machine learning is very amenable to reduced precision. So instead of using FP64 double precision, they go down to things like brain float, bfloat 16. Here we have FP16. Those rates are the same. Already, the FP16 rate is 26.5 versus 2. So a substantially amount more of compute. This is why GPUs are the killer app, the killer hardware for machine learning today because of these things. The difference is that they need to be using vector-like operations. So you have essentially a CPU. which does things like running operating systems, very important, and serial out-of-order processing. And then you have a GPU, which is very good for vector processing. For sciences, well, many of our algorithms are vector-like, but serial components, come into it. And we'll talk more about that in a second. So then the other thing that's kind of exciting about this technology, and I think it is worth noting, well, you have a GPU, you have a CPU, they have memory. I mentioned that, I didn't show it, but the MI50 has 32 gigabytes of memory. It's actually not that much compared to a CPU today. So you have to think carefully about where the memory goes. One thing that's very exciting, this is happening in the supercomputing, and I suspect it'll trickle down to consumers. It's all connected coherently. Has anyone taken a coherency, know what coherency is in an operating system sense? Coherency is when you run in a cache. You have caches in your CPU. You have an L1, L2 cache. So if a number changes in that cache, what happens to the main memory? Does it know that it's been invalidated? Well, it actually emits a signal to say it's invalidated. It needs to update the memory. So it moves through the cache hierarchy. You don't have to, as a programmer, worry about what data you've changed. This system, this is all public, will have coherency between the CPUs and the GPUs. So you have a processing element on the GPU. It makes a change. The CPU will know about it, and vice versa. It's very important, and this is very important because you guys don't care about this, to tell you this because you can start thinking about this as a holistic system. You can program to it. You say, look, I just have a vector calculation. I want you to deal with that. And then you say, well, you don't have to move it back and forth. You say, well, if I need it on the CPU because I'm doing some data processing or something, it'll deal with that too. So it's programmer productivity is something that is actually important at a system architectural level. So what I am personally involved in is the application readiness for these computers. And some of the scale I've been trying to show you is to say that this is going to be a difficult challenge. The labs are very much familiar with this. They have, in fact, what they call CAAR, the Center for Accelerated Application Readiness. And this is an OLCF, Oak Ridge Leadership Computing Facility, which is a group in Oak Ridge that are just designed to try and take applications today and prepare them for this computer. The scale, all the new architectures, things like that are things that they expect they will need to do. Running these computers at scale can cost millions of dollars in electricity alone per year. So they know that every day that the computer sits idle is a substantial expense that they try to avoid. And by doing that, they prepare apps to run from day one. And that's where they pull us in. One thing that's very interesting to note is you see the applications, their goal is to have the applications run with a figure of merit, as they call it, just they choose some problem that's reasonable, and they want it to be a speed up of 4x. And I've already told you the machine is 7 times bigger. And so they've already moved the goalpost down saying, we're not going to get the efficiencies that we would like. We're not getting all the compute out of it. And this challenge is only going to get worse, right? You hear all these numbers in machine learning about 100x speedups and such. Those are often very specific numbers. Look at the whole application, and those speedups are much more modest. And I have a very nice example of that in a moment, I think. They selected these apps, I'll show you in a moment, just based on the science, but also on various other things. The implementation, the models, the algorithms underlying it. They want to have a representative space of applications because they care very much that this be not a one-trick pony, but rather representative of overall the entire computational modeling space. They want development plans. They want people who have well-scoped plans and things like that. So they're very careful about it. But here are the 8 CAAR applications. And you see that the domains range a wide variety of scientific interest, from plasma physics, nuclear physics, fluid dynamics, astrophysics, things like that. And a variety of academic partners that we're working closely with here. I will mention that these applications are open proposals, so be on the lookout. There'll be more. If you have scientific or machine learning codes that you would like to propose for Frontier, you'll have my email after this, and let's talk about it. There'll be opportunities to get on this machine. And it is unprecedented size. So, and of course, no talk would be complete without pretty pictures. So here are some of the examples of these. So CHOIA, the astrophysical simulation there, does a hydrodynamic simulation of galactic modeling. You see that in the middle picture there. Essentially a galaxy moving, some of the mergers that you might see, things like that. Cool physics. The bottom right picture is a picture that I'm very fond of because I worked on this code when I was a graduate student. It's a 3D homogeneous isotropic turbulence simulation. This is more of a fundamental physics investigation into how does turbulence work. A lot of the models that they use for things like designing the Boeing 787, are imperfect models. They are not correct. We make approximations. This simulation is resolving all the features of the turbulence so that we can inform the models better. So that's kind of the way to think of it. But I do want to spend a little time here. These are the apps, and these are a little more of what they're actually running. Give you a sense of what they use in scientific computation. Some of you in this room, maybe most of you, will not know what F90 is, but it's Fortran 90. That is a standard set in the 1990s, of which I suspect someone in this room was not born on that date. There's even a very modern Fortran, or Fortran 2008. So there's some legacy stuff here. But there's also C++. That's really starting to win out, luckily, in scientific computing. But no Python, things like that. No Julia, yeah, things like that. Not yet. Julia is exciting, but not yet. And typically these codes, if you're really playing from home, are C++ 17. We'll see if 20 comes in a little. Wide variety of algorithms, too, for those of you who are computational science people. There's finite volume hydrodynamics. There's spectral methods. There's PIC, particle and cell. Wide variety of algorithms that are represented here as well. All of this is discretized with MPI, if you're familiar with it. It's the message passing interface. This is a common thing in scientific computing for distributed computing. It's also used in machine learning a fair bit. TensorFlow does not use it. Some of the other frameworks like PyTorch do leverage it for multi-node sort of distributed computing, parameter servers and such. These are 8 apps. These are the ones that they're kind of pushing hard on, but there are many more apps. I don't want to give the impression that they're only going to run 8 apps on it. Here's just 12 others that I'm engaged with. Again, computation, combustion codes, high energy physics, cosmology, lots of fun topics in that regard. But so what I want to do is dive into one of the apps. This is NAMD. So I showed you the picture of corona, the coronavirus modeling earlier on. NAMD is a very common molecular dynamics code, so it models the interactions between molecules. It can time evolve these. D. Shaw, for instance, is a company that does this entirely as their business model for their scientific arm. This is a representative workload. It's not the coronavirus one, actually, but it's one I had previously. So what I show you here are, you see there's 3 colors. They're coming through relatively well. This is just a naive examination of the CPU running a NAMD kernel of a relatively common molecule. And you see the vast majority of time, this is a percentage plot, 90% of the time is roughly spent in what they call the compute kernel. They're non-bonded force interactions, if you follow. It's evaluating the potential functions between atoms. And then the rest, well, there's some host computation, so some bonded forces, things like that. And then there's some data transfer type stuff, long-range electrostatics and such. So if you are a developer and you start working on this, 90% of your time is being spent in one kernel. You do what Donald Knuth says. You say, that's the thing I've got to optimize, so let's hit it hard. This is on a CPU, so just transferring it, it's actually very amenable, the bonded forces, to vector operations. Very easy to port to a GPU. You get an 8x speedup, right? The mythical 10x GPU speedup. And so what happens? Well, the bottom now is the plot of the wall clock time. It's normalized again. And so what happened? Well, the compute kernel is still 50% of the time. You've got an 8x speedup. And what's happened is the other pieces are now suddenly intruding into what you've done. This is Amdahl's law in action. What happens is we've had so much success with our compute in the main kernel that the other pieces of computation are now suddenly the bottlenecks, or at least 50% of the runtime. This is a common problem, and it's only getting worse because our compute is accelerating so much, and we're getting so good at computing that all the other things are starting to pop out and really hit us. If you blow this up, the last timeline I showed, so well, how can you decompose it? Well, there's some challenges here. There's the GPU compute, that's still the blue part, and that is GPU compute limited. Well, we can hit that hard, we'll keep just making our GPUs faster. Great. So more high performance double precision operations. But what do you do with the other pieces? Well, some of it are 3D FFTs. If you've studied 3D FFTs, these are typically transposes, so they involve network communication. And they're also then decomposed into 1D FFTs, which are, if you know big O notation, an n log n operation. That's not that much compute. The bonded force kernels are much more like a gem, a matrix multiply, an n cubed, big O n cubed operation. Lots of operations going on, very easy to keep all the compute units happy. N log n, not that much work. It's just a little over linear, right? So when you do this, suddenly memory bandwidth plays a role. So now you've got a different sort of bottleneck in your system. I also mentioned network communication. So now you need to deal with the network speeds, which I mentioned earlier are only going up by a factor of 4 versus a factor of 7. So this bottleneck isn't getting better. Finally, you have still have the red, that's the stuff running on the host. Well, you've got all sorts of other things that might go on there. This is some of it involves host transfers, copying back and forth between devices, which I mentioned we're trying to get better at with coherency and such, but nevertheless is still something that's creeping in more and more. So suddenly you're going to be doing no time on compute, and all you're going to be doing is transferring messages back and forth between devices. Not very efficient, right? So that's just one aspect of these system workloads we're looking at, kind of thinking about the system balance. The next piece of the talk actually is a little bit of a transition. I wanted to talk about the convergence of scientific computing and AI. So if you remember the coronavirus thing I showed earlier, this was using machine learning for an effective sampling of a subspace, right? Couples machine learning with a molecular dynamics simulation. Some very interesting results in the field here. Cosmogan, if you haven't seen it, is using generative modeling to essentially produce synthetic data for cosmological maps. Pretty cool result. That's from Lawrence Berkeley Lab. There have been results in Eulerian flows and surrogate modeling and such. What I want to show you about is some of my recent work, partly as an advertisement. This is done with Octavi Abival, Salas. He's Spanish, and he was a co-op who worked at AMD for a summer. So it's part of the talk where I can say we have co-op positions for those of you looking for summer work. What we did here is we sought to do an end-to-end modeling of the Navier-Stokes equation. So I told you earlier that some of these physical simulations are expensive. So the thought is, instead of solving a coupled set of partial differential equations, three-dimensional equations, Navier-Stokes equations, nonlinear, with a turbulence model, the SA model, we could instead just pop in a machine learning model, train it on actual CFD data, and try and use it, presumably it'll be quicker, and use it to predict turbulent flows. I mentioned the Boeing example earlier. That's kind of a good representation in your head. Many cases, you don't care too much about accuracy. You care about just getting roughly the right answer, within 20% or so, doing that many, many times. Let's say hundreds of thousands, millions of times. So in this case, the thought is, could you use this as a surrogate model instead of solving an expensive PDE? And could you use that then for effective things like subspace sampling, parameter searches, things like that? So this kind of lays that out precisely how we do it here. But on the left, you have an initial condition. There's no fluid flow simulation. There's a nice picture of an airfoil in the middle. And on the right, you have a picture of the fully resolved, the final steady state solution of the flow. This is just a pressure field, but it's not too important. So normally, you just do a physics solver. It might be an iterative solver. It takes n iterations, just solves the physics. On the bottom, what we propose is actually, and this is something, as is typical of these talks, you show the final state versus what you started with. But we do the physics solver for a few iterations. It's called k iterations. This is called a warm-up. You then use this deep learning model that has been trained in an inference mode. It takes the input image. It spits out what it thinks the final is. And then you use the physics solver for a few more iterations, kind of a refinement at the end. The reason for this, that you can say, a posteriori reasoning, is that the warm-up, well, when we give it the input conditions, it doesn't really know what those boundary conditions are. They're not codified at all. You could embed those in the machine learning model. I'll talk about the architecture on the next slide. But there's no reason to do so. In fact, we found that unsatisfactory. What we want here is a model that we can plug into any physics package. No knowledge of the physics required. So we give it a few iterations. It gives it a sense of that boundary layer. It's starting to resolve the flow. It sees where, for instance, the velocity is 0, where the compressibility should be 0, things like that. So then you give it to the inference. It spits out something. But it still doesn't actually satisfy all of the physical laws that we know to be true. For instance, the velocity at the wall might not be quite 0, might be very small. So the physics model in the final few iterations really imposes those physical constraints. And when we do this, as I'll show, we get substantial speed-ups. So this is a way you can kind of push your neural net button, and you will speed up your simulation. It'll be quicker. And yet, it actually fits all of the convergence criteria of the physics simulation to begin with. Still satisfies incompressibility. It still satisfies, let's say, a 10 to the negative 6th convergence criterion, all that. So if you were, I claim, to have a black box between these, and you were to run your physics simulation, you wouldn't know which one I had run. You wouldn't be able to tell. So no talk on machine learning is complete without a picture of convolutional layers. This is the network architecture. So it's a relatively shallow in the parlance of deep learning. It's 3 convolutional layers coupled with what I hate to call deconvolutional layers, because they're not deconvolutional layers. This is the part of the talk where I rant. They are transposes of the matrix, of the weight matrix. That's not a deconvolution. D would be the inverse, right? If you've taken linear algebra, you should know that. So don't do it. It's not in the paper, but it's for brevity, I put it here. But so there's 3 layers here. You start on the left. There's the initial condition. These are fed in as essentially images. A velocity field can be thought of as just an image in this sense. You move it through 3 convolutional layers. You see that we use kind of standard activation functions like hyperbolic tangents and such here. And at this point, you've reached the middle, the yellow here, which is the projection operator to essentially a latent space. So you have some latent representation of the physics that's being represented. In a classifier, this might just be a 1, where you say, yes, I think it's a cat. In this case, we believe it corresponds roughly, and I hate to use the word learning here, but that the network has learned some features of flows that tend to be characteristic. For instance, that near walls, the velocity should be 0, etc. But this is very closely related, and this is why I mention it, to generative methods, autoencoders, and such that are very, very popular right now. So then you follow from the latent space to a projection back to the forward in time, which goes through what we could call these deconvolution operators, and it spits out what it thinks the velocity field should look like. By the way, this is all the fields, so I should say in addition to the 3 components of velocity, it also spits out the pressure field, energy fields, things like that. So it's a complete end-to-end package. This neural network architecture is used for all of them. It's consistent with that. So again, it has no knowledge of the physics. I should be fair. So the question is for transient flow. It's a great question. We haven't done it yet. So this is all steady. That's future work. I think that there's a variety of ways you could look at it. Maybe we should take that offline. But that's something I'm very eager to look at. Yeah, it's a good question. But this is steady. The training data. So on the top, I have what are a series of ellipses, and then the testing data, which are an airfoil. It has not seen this. It has not been trained on it. It's been trained on things similar to an airfoil in geometry, but not quite the same. So this is a mildly extrapolative state. It's extrapolating a little to something it's never seen. In particular, you see I highlighted in red the trailing edge of the airfoil, which is certainly not elliptic, and has important repercussions if you're familiar with fluid dynamics, such as separation, pressures, and such. And then there's an ellipse, which it has seen. It has not seen this particular eccentricity of ellipse, so it is an interpolation. Between 2 it is seen. And then finally, a cylinder. So what we're doing here is trying to test it on conditions it hasn't seen before. So this gets back to the question at the beginning, how do we have confidence in our predictions? Well, we can look at it in different regimes. Regimes in which it's been extrapolated, it's going to do the worst on those because everyone does worse when you extrapolate. Cases where it's seen it already, well, it nails those. And then cases where it interpolates. It hasn't quite seen that case, but it's seen cases around it. And the results, it will come as very little surprise, are good. So this is the velocity field for the channel flow. So in this case, on the top and the bottom, it's like a pipe. There are walls. And then the flow, so A is if we do this with no refinement. So we actually just use the model, see what it spits out. B is where we use it with this final refinement, where it actually reaches, it reuses the physics solver at the end. And then C is the physics solver itself. By eyeball norm, you're not going to see a difference here. D is where we actually difference between them, and you see that the absolute error is, in many cases, substantially less than 1%. Yeah.
So a couple of slides back, you showed on the top you have the physical solver, and below you have in between you put the neural network.
Yes.
It's not clear to me how you train that. Because the input out and the architecture you have later on the same, right?
That's right. And yet, all we did is we trained it on the final states. So, and I should have actually added that slide. So we give it we sample. So we have an iterative solver, and I'll show you. It takes a few thousand iterations to converge. Let's save those iterations before convergence, and then we'll give it the final state. The final state is the truth. That's what you're trying to minimize, and then the input data, the training data itself, is those iterations leading up to it. Yeah. But it is a different in that sense. The pressure field, very important if you follow this. Again, this is slightly interesting that you see it doesn't nail it. It's slightly different. I don't have a diff on this, but this is a area that's harder to get. It is a harder condition to impose in these solvers. If you're familiar with CFD, you know that pressure is the hard part. It doesn't nail it. It does pretty well. So it's interesting. It learns the velocity field exceptionally well. Doesn't calibrate so that it can do that. Lots of reasons that it might work or work not. Maybe it just needs more capacity, more layers. That's the typical trend in deep learning is to just throw more layers at it. I find that unsatisfactory, but nevertheless, this is where it's slightly weak. So accelerating convergence. So here are the plots of some of the results. This is what the case we called, and it's not particularly useful, but the observed geometry, different flow conditions. So this is where we said, this is essentially a verification test. We test it on cases it's already seen before. It's been trained for it. How well does it actually get it? And how much does it speed it up? So not unexpectedly, you see that it gets about a 7 times speed up. So it goes from about 1,500 iterations in the CFD to only requiring to less than 300. So big speed up. And again, it's meeting all the convergence criteria that you had before. You could imagine you've run a code before. Your network is trained on it. You want to run it again for a slightly different case. The flow conditions, the Reynolds number has changed. Minor changes like that. And suddenly you say you could just use your neural network for it. It would be a speed up, right? This is not an unprecedented mode to run in for engineering problems of interest. So you have a database of runs you've already done. That would be a useful case. This is a harder case. Now this is a subset of the velocity, or the geometry, excuse me, the same flow conditions. So we don't change the flows, but now we change the geometry it's been trained on. It's been trained on one geometry, it has to run on another. This is the interpolation case I showed you before. The speed up is more modest. What that means is that, well, you're not giving it stuff it's already seen precisely before. It's now guessing a little more. It doesn't perfectly represent the results. It certainly doesn't perfectly represent the Navier-Stokes operator, the underlying mathematical operator. But nevertheless, the speed up is still 3.5x or so. So it's a not insubstantial speed up. And again, because of the way we do it, where we have this final iterations on the solver, it still satisfies all the physical constraints that it needs. It's just the speed up is more modest. And then finally, the one that you all came for, the extrapolation cases. You're still, in many cases, getting 50% 2x speed ups on both airfoils and the cylinders. Those are the cases it's never seen before. There's still modest extrapolations. I don't want to oversell this. These aren't wildly different geometries than it's seen. But it is maintaining everything it did before and yet giving an appreciable speed up for it. So again, from your perspective, you could be running a CFD code. A Boeing engineer could be doing optimization on this. They would probably have confidence running this, and a 3x speed up might be enough for them to say this is a big win to them. So I think this is a very exciting result. It's very in keeping with what's going on in machine learning and AI when coupled with CFD here, but scientific computation in general. You don't expect these things, as I joked before, to just replace your jobs. That's not what the purpose is. But as using it as a surrogate model, replacing computationally expensive physics, using it in very specific ways, that's a great place for it. And so I see this again as a trend that you should be aware of. By no means do I think that we will not know what PDEs or physics is in the future, but I do see this as a method of supplementing scientific computation, particularly for optimization and such. But so someone mentioned it. I think there's a variety of ways this could go. I'm very excited in continuing it. Unsteady flows, looking at other turbulence models and regimes. I think that's actually of less interest. I don't see any particular reason the Szilard-Almaras model was better or worse than others. And then the other area that I'm particularly interested in is physical domains. We've done it for CFD. That's because of my background. but looking at, for instance, molecular dynamics simulations, can we use this general architecture for many different cases? And in transfer learning, which is common in machine learning, you have trained weights that have learned certain features, and then it accelerates the training of a network when you apply it to a new domain. There's reason to be optimistic maybe that would work here too. So you might have a general network architecture and you could pull it down and train it for your own particular physics, and it might take only a little time to train it, which would be very exciting. The final area I'll mention is there's no reason you couldn't apply this to more abstract mathematical abstractions. That's something I'd like to look at, thinking about iterative solvers, multi-grid in principle, very similar to the process we're looking at here. So I only have 10 minutes, so I will just throw up my conclusions. You know, I tried to take you on a talk through what we're doing with the supercomputing, but then try and tie it back to some of the applications and the domains and how things that I think will hit scientific computing in the next decade, let's say. And some of those include these heterogeneous architectures, a lot of the different programmability. It's going to get very hard. Those free wins are not going to appear anymore. You're not going to just buy a new CPU. And this in turn will be an opportunity. There'll be new algorithms, new approaches that you can look at there. Lots of good papers to publish there. And it will actually involve focusing on how you couple with the hardware. And that's obviously, you know, to come full circle, my role at AMD as a computational scientist. I work with a lot of hardware architects who do not know what their hardware is used on. And tightening that loop is a very important thing. And I think data scientists will be looking at this as well. You won't just build a data center. You'll build a data center for a specific purpose. And similarly, we're doing that with the supercomputers today. So think about that kind of architecture as you go off in your careers that way. So I'll end with that. I'm happy to take questions. I have my email if you think of something later and you had a good retort. And then I do have Frontier stickers if you want one for your laptop. So you can go. Thank you.
Thank you, Nick, for the great talk. We can have a bunch of questions here. Go ahead.
For my own back-of-the-envelope calculations, can you tell us how many nodes will be in the cache on Frontier?
No, I can't. No comment is what I'm supposed to say. Sorry.
So you mentioned the trend of integrating ML with scientific computing original algorithm. Do you see any new challenges to hardware? Like what are the modifications? Can you give some examples that motivate new hardware designs because of that integration?
You know, to take it even one step further, you know, and I didn't put it in this talk because it's become a cliche, but Moore's law is ending. You know, we are not getting the free wins on transistors we used to. We are special designing our hardware. And yet everything I said here was to say, let's be more general purpose about our algorithms and our approaches. So those are two completely opposing forces. I think it is clear, you know, that for instance, our competitor NVIDIA is developing devices that have tensor cores on them, which are specialized machine learning hardware. There have been many attempts to leverage that for HPC, and it hasn't worked so well, in my opinion. So I think the answer is still general purpose. We have to architect carefully our designs so that we will reach the broadest base. I think the labs do a good job of covering the physical regimes, but internally at AMD, what we look at is a much broader basket. It's things like that, but it's also ResNet 50. It's also Transformer. Try and capture what are the motifs, the computational motifs that we can really leverage.
Do you know why tensor-specific design may not work well?
Well, you know, if you look at, for instance, the Google TPU, which you may have heard of, that is a systolic design. It's much more like an actual matrix operation versus a vector. There are pros and cons to this. If you the problems that I encounter in the NAMD example will be pervasive in the TPU. It will work very well for convolutional operators of certain size, and it will work very badly in a week when someone decides convolutional operators are useless. And at the rate machine learning is moving, in particular, but even scientific computation, I would be very hesitant to inscribe in hardware, which takes many years to do and design, something that focused. I think general purpose, but vectorizable is the right way to go, personally. Yeah.
How are you measuring megaflops? Are you using LinPack or what?
Yeah, that's a good question. I wanted to talk, and I just didn't have time. But so, great question. When I showed the pictures here of how these computers are actually measured, I did show the peak. I did not use LinPack. So the question is, LinPack is a, sorry, see if I can find the slide. LinPack is essentially doing matrix multiplications. Oh, sorry. One more. So these numbers are the peak numbers. They are the rated capacity of the device. No application will ever hit that, let's be clear. You will get some efficiency out of it, and that efficiency is, let's say, 73% on Summit if you do the math. So they're only getting 73% of this number here. Similarly, I show you this big ol' number here. We're not going to hit that number on any real application. But if you were to say, let's hit 73% on HPL or high performance LinPack, that would be a reasonable rough estimate. So for those of you who don't know, the top 500 list does not just take your word. If someone says my device runs at 10 exaflops, they don't believe you, they have to measure it. And we measure this empirically with a standard data set or standard problem, which is called high performance LinPack, which largely just does matrix multiplies of a very large nature. It makes it pretty compute bound. So it tends to be a very nice and flattering portrait of the computer versus the reality. Most apps will be lower than HPL.
Yeah, I have an architectural question. So NVIDIA acquired Mellanox, right?
Yes.
And you can now direct DMA into the global memory of the GPU by going over, but I think it's only PCI 3, right? Because it's Intel limited.
That's right.
And then in their unified memory architecture, you can go back and forth, but underneath the hood, it's still going over PCI 3, right? So you guys have PCI 4 in a different topology. So sort of what's going on under the hood, and what's your sort of interconnect DMA sort of ecosystem?
I'm so glad you asked. Good question. We have what we call Infinity Fabric. This will be a PCIe Gen 5 compatible, but it will be substantially higher bandwidth. It's internal to AMD, and the other key thing here is that it will connect between both CPUs and GPUs. So it'll allow for a coherent memory space between both CPUs and GPUs.
Yeah, but between the HBM and the GPU and the regular DDR and the CPU, is it still going over the PCI bus, or do you have a separate path for that?
Yeah, and so this is, NVIDIA has not done us a service with this unified memory statement, because to me, unified memory means it's a global address space. That's what it should mean. And that's not what it means right now. There are a variety of ways that it occurs in NVIDIA hardware today. Those can be explicit copies over the PCIe bus, where it just migrates the whole data structure. So I've got a data structure on my CPU, and the GPU says, I really like to use it, and it just copies the whole thing over PCIe. As I think you're implying, that's very inefficient. The coherency I'm talking about here is different. It's much more fine-grained. It's much more like a C++ coherency model, if you're familiar with that. What is happening here is that it will require a 0 copy. So again, like a cache line, you can just pass an invalidation, which will say, this cache line has been invalidated in this data structure, and then it will pass, let's say, a cache line to it. So it's a much smaller message size. It's not the full buffer you need to move. That's how it works in caches, because that's more efficient. Now, if you want, it's like they say, if you like your doctor, you can keep your doctor. If you want your migration, you can keep your migration. There will still be ability to explicitly migrate data, and then there'll also be kind of this, this CUDA memivise, if you're familiar with it. There'll be similar things to that. So it'll still move them if the thought being here, if you once in a while just pap the CPU and say, I need this updated data structure, that's great. If you're doing it constantly, you're going to see the PCIe bus. You're going to see whatever your connection is, no matter what. There's no way you can architect yourself out of that. At that point, the software should say, this guy keeps asking for it. This person keeps asking for it. Let's just move the whole data over. And that's where it should reside. But how you choose that, is it 5 times, is it 1,000 times? That's a little bit more of a clever tuning parameter.
One more question, I think. Yeah, go ahead.
Yeah, I wonder, what's the sort of flop you can achieve with the classic CFD solver and with the CFD net? Because, my impression is that those classical numerical methods, like finite volume, finite difference, they have pretty low compute memory ratio.
Yeah.
So the flops are typically would be much lower than a computational neural network. I'm wondering, do you sort of achieve a much higher machine utilization by adding machine learning into
See, it's a great point, and that's part of the motivation here. Is that if everyone got that. Most CFD solvers, just in general, are memory bound. They don't have very big stencils. They have very few flops per load, if you think of it a memory system ratio. Deep learning has been carefully constructed in part to fully utilize the device, very much use the ALUs. It's very flops. The number of flops per memory load are very high. So methods like the machine learning one are, in some sense, computationally more efficient. So I don't know if that answers your question, but I agree with the spirit of it, I thought, or at least the gist I got.
What is like the number? It's like what's the percentage of the flop you can achieve with the original model?
With the model I showed, it achieves well over 90% utilization of the device. If you were to do the same thing, I have not measured it for the CFD, but it would look like the memory system. So yeah, it's doing a lot more as a result. I think that's a powerful part of the technique.
Thank you very much, Nick. Let's thank Nick.
Yep. Thank you.